A chaotic repeating signal often appears completely unpredictable, but that jagged shape can be seamlessly deconstructed into a stack of uniform, smooth sine waves. Any periodic waveform, anything that continuously repeats itself over a set interval of time, can be expressed mathematically as a Fourier series. The math only works if the signal satisfies three rules, known as the Dirichlet conditions. First, if the wave is discontinuous, it is limited to a finite number of discontinuities within a single period. Second, it must maintain a finite average value across that period. And third, the wave is limited to a finite number of positive and negative maxima, its peaks and valleys. When a signal meets these conditions, we can build its Fourier series using the baseline trigonometric form. This master equation relies on three distinct components. It begins with a constant for the DC average value, adds a sequence of even cosine waves, and finishes with a sequence of odd sine waves. This trigonometric equation acts as a universal translator, converting a raw time domain signal into a precise recipe of component frequencies. To accurately assemble that recipe, we have to calculate the specific weights, the AN and BN coefficients, for every single harmonic. The standard method for finding these weights requires evaluation integrals. These definite integrals compute the area under the curve across one full period, represented here by t. Alternatively, we can integrate with respect to the electrical angle over 2 pi radians, which is often simpler. Evaluating these complex integrals for dozens of individual harmonics is a computationally expensive and tedious process. If brute force calculus is too slow for practical engineering, we must find a way to bypass these integrals to save processing time. The easiest way to skip the calculus is by analyzing the physical geometry of the waveform. Look at the sawtooth wave in Figure 15.2 to test this approach. The first term of the Fourier series, the 1/2 A0 term, represents the DC average value of the entire signal. By visually inspecting the graph, we see it rises linearly from 0 to 10. The midpoint, or average, is exactly 5. We have defined the first term without solving a single integral. While finding the constant was straightforward, calculating the fluctuating AN and BN harmonic terms for this sawtooth still demands full integration. Visual inspection solves the average, but we need a stronger geometric tool to eliminate the difficult harmonic integrals. That tool is waveform symmetry. It allows engineers to mathematically erase entire halves of the Fourier equation. Consider these two variations of a square wave and notice how they align with the vertical y-axis. Graph A demonstrates even symmetry. The left side is a perfect mirror reflection of the right side across the axis. Because an even wave is perfectly mirrored, it is composed entirely of cosine terms. Every single sine term, the BN coefficients, instantly drops to 0. Now look at the second variation in graph B. This demonstrates odd symmetry. The wave is inverted across the origin. Where the right side goes positive, the left side goes identically negative. The mathematical payoff is the exact inverse. An odd wave is composed entirely of sine terms, meaning every cosine term instantly equals 0. Symmetry is a choice. By strategically placing the 0-time axis on a repeating signal, we can force that signal into an even or odd state. We can also look for half-wave symmetry, where the negative half of the cycle mirrors the positive half, guaranteeing all even harmonics are completely absent. By recognizing symmetry, engineers turn grueling calculus into basic geometry, cutting their mathematical workload exactly in half. Even with symmetry, the trigonometric format remains cumbersome because it requires tracking 3 separate coefficients for every single harmonic. Euler's formula provides the bridge to a cleaner mathematical architecture. By substituting the sine and cosine terms with their complex exponential equivalents, the series transforms entirely. This substitution lets us collapse the messy algebra into a brand new complex constant, labeled AN. The AN term mathematically fuses the amplitude and the phase angle of a harmonic into a single expression. This reduces the calculus workload significantly. We now only need to solve one master integral to map the entire series. Instead of balancing 3 separate evaluation integrals to find the trigonometric values, this single formula defines the complete state of the wave. The exponential form acts as a streamlined mathematical engine, and its supreme efficiency directly powers all of modern digital signal processing. Complex constants make the math elegant, but we need to see what these coefficients actually look like in physical reality. We map them using a line spectrum. This chart plots harmonic frequencies along the x-axis against their amplitudes on the y-axis. For waveforms with sharp discontinuities, like the sawtooth, the spectral plot reveals amplitudes decreasing very slowly into higher frequencies. To maintain mathematically sharp edges, the spectrum requires significant high-frequency energy, pulling heavily on harmonics well past the 10th position. Contrast this with the spectral plot of a smooth wave lacking any sharp discontinuities. Here, the math converges rapidly. Any harmonic energy past the 5th or 6th position drops off and becomes physically insignificant. This defines the stakes for physical engineering. To transmit a signal with sharp, jagged edges, every component in your system must be capable of handling those high-frequency harmonics. If the system's bandwidth is too narrow to pass those frequencies, the signal rounds off and loses its data-carrying shape. Fourier analysis exposes the fundamental energy and bandwidth limits of the physical world, revealing that every signal shape carries a specific cost in frequency.